In this section, Chapter 4, Section 4, we're going to be looking at oxidation-reduction reactions. And oxidation-reduction reactions are simply reactions in which one thing loses an electron and something else gains an electron. So the thing that loses an electron we say that it has been oxidized, and the thing that gains an electron we say has been reduced. The example that's given up here, the picture that's given, has, calcium metal. So these are calcium turnings, and calcium's quite reactive. It will react with oxygen that's in the air, or if you had just pure oxygen above it, it would react quite readily. The calcium would give up 2 electrons per calcium atom, and the oxygen would accept those electrons to become oxide, so it would become O2 minus. Of course, the calcium and the oxide would end up forming an ionic compound, and so we get this sort of whitish colored, chalky looking compound, and that is calcium oxide. So that's an example of a redox reaction or oxidation-reduction reaction. So let's look at a redox. Again, redox is just short for oxidation reduction. So a metal can get oxidized, and when a metal gets oxidized, for example, sodium, it can get oxidized to form sodium plus 1, so it has lost an electron. Chlorine, so chlorine gas has an oxidation state of 0, and it can gain electrons to become chloride. So that is an oxidation reduction example. So we want to look at a set of oxidation states, a set of rules for oxidation states. Oxidation states are assigned to atoms as a bookkeeping tool to help us balance redox reactions. So sometimes it's really obvious when you have something that is an ionic compound and you can tell what the charge on each thing is, then you know right away what the oxidation states are. However, in other compounds, it's a little less obvious. And so we use the rules for oxidation states as a way of helping us to determine what has been oxidized and what has been reduced. So if we have compounds that are covalently bonded to each other, then the oxidation state will tell us what the charges would be if the shared electrons were assigned to the more electronegative element. Again, electronegativity is something that increases as you go up and to the right towards fluorine, so we'll just kind of leave it at that. Since we haven't really got the rules for electronegativity down perfectly, I'm going to give you a set of rules that should get you through 99+% of all the compounds that are out there if you follow these rules. So let's start with the first rule. And the first rule, and by the way, you can find this set of rules in a document that's called Oxidation States, and it is on eCampus. So oxidation states, rules 1 and 2. The first rule is if you have an element and that element's not bonded to anything else and it doesn't have a charge on it, then that element has an oxidation state of 0. So elements that are 0 have a neutral charge have an oxidation state of 0. If you have a monatomic ion, and a monatomic ion is an ion that you can tell what its charge is. That's all it is. If you have a single ion and you know what its charge is, then that's a monatomic ion. And whatever its charge is, that's its oxidation state. So monatomic ion, it's just the charge. So for example, if you've got magnesium that's in a compound, it's going to be magnesium 2+. It will have an oxidation state of +2. Same thing here with sodium and chloride. You'll see that they have oxidation states of 1 and -1. So to go back to that example we just looked at a minute ago, Sodium here has an oxidation state of 0, and here has an oxidation state of +1. Because it gets more positive, we would say it's been oxidized. Chlorine here has an oxidation state of 0 because it's an element, and here it has an oxidation state of -1 because of the negative charge. We ignore the coefficients when we're looking at oxidation states, by the way. All right. Our third rule for oxidation states is for oxygen. And oxygen, the oxidation state of oxygen is usually -2 if it's in a compound. And water, calcium oxide, sodium oxide, any number of compounds that we're going to look at, that's going to be the case. The exceptions are when we have compounds where oxygen is bonded to itself. And that's going to include peroxides and superoxides. So peroxides and superoxides. But most of the time, it'll have an oxidation state of -2. Oxygen, oxidation state rule number 4 is for hydrogen. Hydrogen in most compounds is going to have an oxidation state of +1. And so many of the compounds that we're used to seeing and all the ones that I have listed here have an oxidation state of +1. The exception is when it's bonded to something less electronegative, which usually means a metal. So if you have hydrogen bonded to a metal, then we typically will call it a metal hydride, like sodium hydride or calcium hydride. Anything where you call hydrogen a hydride, it's going to have an oxidation state of -1. But like I said, most of the time it'll be +1. All right, rule 5, halogens. Most of the time, halogens have an oxidation state of -1 if they're in a compound. And for fluorine, there's no exceptions. It's always -1 for fluorine. And that is because fluorine is the meanest, baddest, most electronegative element on the whole periodic table. It always gets the electron. Always. Fluorine, what a pain. All right. For the other halogens, chlorine, bromine, and iodine, we will find that they usually have an oxidation state of -1 unless they're bonded to something more electronegative. And really, the only things more electronegative are going to be a halogen that's above it or oxygen. Now, sometimes nitrogen, but that's rarely going to be the case. But so usually, if it's bonded to a halogen above it or oxygen, then it could be something else. All right. And then rule 6, I like to call rule 6 added up. And what that means is if you've got a compound, a neutral compound, then the sum of all the oxidation states in that neutral compound comes out to 0. If you've got a polyatomic ion, then the sum of all the oxidation states in the polyatomic ion equals the charge on the ion. All right. I have another slideshow, which I already have pulled up. And then after we do some of that slideshow, we're not going to do the whole thing because it will take too long. But I have another slideshow. And in that slideshow, we're going to look at names and oxidation states. Now, usually I have students do the names, and then eventually I have some of the students do the oxidation states. But all right, let me find it here. There it is. It is my Supertastic oxidation number and compound name review. You will find this on eCampus next to the Chapter 4 PowerPoint presentation. All right, and I have another little document here that I wanted to include. And I'm going to put it here. Let's see. There it is. So I have written down sort of the short version of each of these rules. If it's an element, it's 0. Monatomic ion, it's the charge. If it's oxygen, it's usually -2. If it's hydrogen, it's usually +1. If it's a halogen, it's usually -1. And that you have to add it up. And usually what you'll do is you'll go through this list in order, always keeping in mind the final rule. So always keeping in mind that final rule. All right, so let's do the first one. All right, this, of course, is chlorine. And we ask ourselves the question, is this an element? And the answer is yes, it's an element. That means its oxidation state is 0. That also means we're done with this, right? We're done with this particular one. So anytime you have a neutral element, it has an oxidation state of 0. Next, and we don't have to do any more on that particular one because we've figured that one out. So next, this one is CaO. That, of course, is calcium oxide. Calcium oxide, there's the name, so calcium oxide. So if we get past, is this an element? And the answer is this an element by itself? And the answer is no. Then I kind of jump ahead to rule 6 and I say, well, what is this, a neutral compound or is this a polyatomic ion? And this, as you can see, is a neutral compound. And so that means that the sum of all the oxidation states, when we add them up, has to come out to 0. So our total charge is equal to 0. All right, so now that we've done that, we'll look at, is there a monatomic ion present? All right, and the answer to this is yes. In fact, there's 2 monatomic ions, and we know the charge to both of them. But we will do calcium first because calcium, here we go, calcium is in group 2, and we know calcium is always plus 2. So calcium is always plus 2. So we're going to put a positive 2 over that calcium. Now, the next step that we're going to do is we're going to take that 2 and multiply it by the number of calcium atoms. In this case, there's only 1, so positive 2 times 1 is positive 2. That's not particularly hard. Now, here's how this works. Since we have 1 element left, what we need to do is we'll take 2 plus some number is equal to this number over here. So positive 2 plus some number equals 0. Well, clearly that some number has to be negative 2. Then when we're going up, because we want to get the oxidation state up here, this is just the oxidation state multiplied by the number of atoms. We're going to take this and divide by the 1 oxygen atom, and that will give us an oxidation state of negative 2 there. Okay, so our oxidation state for calcium is positive 2, and for calcium is positive 2, for oxygen is negative 2. All right, next, this is called sodium oxide. Now, if you're going along doing this and you're a little rough on the names, every time I get to a new name, pause before I say the name. Like pause the video before I say the name and try to figure it out yourself. All right, so this one is sodium oxide. Sodium oxide is a neutral compound, so it's going to have a total charge of 0. You can tell it's a neutral compound because we don't have any charge listed right here. So total charge is 0. So now we need to look. We already know it's not an element by itself. Are there any monatomic ions present? Well, yes, sodium is present. Now, oxide is also present, but sodium is present. Sodium is in group 1, and group 1, as we know, always has a positive 1 charge. So we'll put positive 1 over the sodium. We're now going to take that positive 1 and multiply by 2, and that gives us positive 2. Since we only have 1 element left, we can now figure it out by context what the oxygen must be. Positive 2 plus some number gives us 0. Clearly, that some number has to be negative 2. And then negative 2 divided by the 1 oxygen gives us negative 2. So there we have the oxidation state of both sodium and oxygen in sodium oxide. All right, next. I'll give you a second to answer this one, what the name of this is. Hopefully you said nitrite ion, and that is correct. All right, so this isn't an element by itself. We're going to again jump ahead to Rule 6, and Rule 6 tells us that the sum of all the oxidation states comes out to the charge. Since this is a polyatomic ion, then the charge, and we look at the charge here, it's negative 1. So the total charge is negative 1. So our sum of all our oxidation states has to come out to that negative 1. So now we'll go through our list. Is a monatomic ion present? And the answer to that is no, there's not a monatomic ion present, so we're going to skip that. If this had been like sodium nitrite, then yes, there would have been a monatomic ion, but we're just looking at the polyatomic ion by itself. Is oxygen present? Well, yes, oxygen's present. So finally, if you get down to this rule and oxygen's present, it's probably -2. Now, I'm sure there's some exceptions to that, but it's probably going to be -2. So up here, we'll put -2 above the oxygen. We'll multiply -2 times 2, and of course, that gives us -4. And here is the hard math problem, and I'll put hard in quotes because it's not that hard. Some number plus -4 gives us -1. Well, clearly, that's going to have to be +3. +3 divided by the 1 nitrogen gives us +3. So the oxidation state of nitrogen in nitrite is +3. Now, write that down. Put down nitrite, put down NO2 minus, and then above the nitrogen, put +3, because on the next one, we're going to compare this. Okay. So our next one is NO3 minus, which, as you probably know, is called nitrate. That is correct if you said that. If you said something else, then you were not correct, but I'm sure you will get better at that. So that is the nitrate ion. And for, let's see, for nitrate, all right, so the total charge is -1, right? Kind of jump ahead to rule 6. And now let's go through our list. Is a monatomic ion present? No. Is oxygen present? Yes, oxygen is usually -2, so we're going to put -2 up there. -2 times 3 is -6, so we'll have a -6 there. And that gives us a total charge of -1. So some number plus -6 is -1. Well, that some number clearly has to be +5. So +5 divided by the 1 nitrogen gives us a +5. Now, go and look at the nitrite that you have written down on your piece of paper, and you'll see that the oxidation state of nitrogen in nitrite was +3. The oxidation state of nitrogen in nitrate is +5. Well, what that means is that the oxygen in the nitrogen that is in nitrate is more oxidized than the nitrogen that is in nitrite. So it's more oxidized, and it has a higher oxidation state. It is not a coincidence that there are more oxygen atoms connected to it. Okay. So now that we've done that one, let's do another one. All right, this one is lithium nitrite. Hopefully you're able to get that. This is a neutral compound. It is an ionic compound. It's a neutral compound, and because it's a neutral compound, our added up rule is going to give us a total charge of 0. Anytime you have a neutral compound here, then the total charge is equal to 0. So we'll go through our list. We already know this is not an element by itself, it's a compound. Is there a monatomic ion present? And the answer is yes. Lithium, and I'm going to bring my periodic table over, lithium is in group 1. We know that it's always got a charge of +1. So we're going to put a +1 over the lithium. Well, new +1 times 1 is +1. Now, when we look at a compound, and we've just got one of the oxidation states, if we have just one left, then we just have to figure out what that other one is. If we have 2 left, then we need to go back to our rules. And so here we've figured out, had a monatomic ion, we gave it that one. Next, does it have oxygen? Well, yes, it does have oxygen. And the oxygen has an oxidation state of -2. Well, an oxidation state of -2, -2 times 2 is -4. So here what we can do is +1 plus -4 plus some number gives us 0. Well, that some number has to be +3. We'll take the +3, divide by the 1 nitrogen, and that will give us +3 as the oxidation state for nitrogen. Okay, so quick note here. If you look at nitrite that you had a minute ago, you saw that it had an oxidation state for nitrogen of +3. Here in lithium nitrite, it also has an oxidation state of +3 for the nitrogen. And really, it does not matter where your nitrite is. your nitrite will always have an oxidation state of +3 in nitrite. So the nitrogen in nitrite will always have a +3 oxidation state, whether it's in a compound, whether you look at the polyatomic ion by itself, or whether it's even nitrous acid. It'll still have a +3 oxidation state. And that's something that you can use to your advantage if you get a more complicated compound than you're ready to deal with. And I can show you an example of that a little bit later. Okay, so next one. This is called ammonium. That is correct if you said ammonium. So that is the ammonium ion. And we already know that this is not an element by itself. And since it's not an element by itself, we need to get the total charge. We add it up. Well, the total charge is +1. So the sum of all the oxidation states also has to come out to +1. Now, since it's not an element by itself, we need to look, is there a monatomic ion present? And the answer to that is no, there's not a monatomic ion present. This is just a single polyatomic ion all by itself. So next, is oxygen present? Well, no, there's no oxygen in this polyatomic ion. So next we'll look at hydrogen. Is hydrogen present? Well, yeah, there's hydrogen. So we're going to put a +1 above the hydrogen. We'll do +1 times 4. Of course, it's +4. No need for a calculator here. And some number, since we only have one element left, we're now ready to solve for nitrogen. Some number plus +4 gives us +1. So that some number, of course, has to be -3. We'll take the -3 and divide by the 1 nitrogen, and that will give us -3 as the oxidation state for nitrogen. All right, our next element, our next substance here. This is PO3 3-, which of course is phosphite. Yes, so that is phosphite, the phosphite ion. This is a polyatomic ion, so we'll need to look at that charge, which is -3, which means the total charge is -3. Okay, so is there a monatomic ion present? No. If this were like lithium phosphite, then we would say yes, but this is not, so no. Is oxygen present? Yes, oxygen is present. Oxygen usually has an oxidation state of -2. So we'll do -2 times 3 is -6. Now, since we just have the one element left, we don't need to look at our list anymore other than add it up. And we just need to figure out what the math problem is here. So some number plus -6 gives us -3. Well, that some number obviously has to be +3. So +3 divided by the 1 phosphorus gives us a +3 oxidation state in phosphite. All right. After you do enough of these, you will be able to do these pretty easily by yourself. So next, we have SO3 2-. Well, this is called the sulfite ion. So that is the sulfite ion. So we'll do sulfite. Total charge is -2. So we'll put -2 over there. Let's look, is there a monatomic ion present? And the answer to that is no. This is a polyatomic ion, and there's no monatomic ion present. All right, is oxygen present? Well, yes, oxygen, of course, is -2. -2 times 3 gives us -6. All right, and so since we have just the one element left, we will do some number plus -6 gives us -2. So some number plus -6 gives us -2. Of course, that some number has to be +4. And then we'll do +4 divided by the 1 sulfur, and that gives us +4. So the oxidation state of sulfur in sulfite is +4. All right, next, HSO4-. Well, this is called bisulfite, or sometimes called hydrogen sulfite ion. So either of those are correct. This is one of the polyatomic ions that I've asked you to memorize. And if you look, the total charge here is -1. So that is the sum of all the oxidation states will have to come out to -1. We'll look at our list. It's not an element. Is there a monatomic ion present? No. Okay. Is oxygen present? Yes, oxygen is present. We'll put a -2 there. -2 times 3, of course, is -6. All right, since we have 2 elements left, we'll need to go back to our list. Is hydrogen present? Well, as it so happens, yes, it is. So +1 there. +1 multiplied by 1 is +1. All right, since we only have 1 element left, we're now ready to solve for sulfur. So +1 plus -6 plus some number gives us -1. And that some number, of course, has to be +4. We'll do +4 divided by 1, and that gives us +4. So the oxidation state of sulfur in bisulfite is also +4. If you go back and look at that previous one, you saw the oxidation state of sulfur in sulfite was +4. Well, here in bisulfite, it is also +4. All right, if you looked in sulfurous acid, it would also be +4. If you looked in sodium sulfite, it would be +4 for that sulfur. So once you figure out what it is in a particular series, you'll know what the oxidation state is always. All right, now, of course, for sulfate, it would be different. Let's look at another one. So this one, you may not have the name down for this one yet, but this one is called iodate. That is the iodate ion. It is a polyatomic ion, and the total charge here is -1. So with -1, we're now ready to go through our list. Is a monatomic ion present? No, it is not present. Is oxygen present? Yes. Oxygen is present, and it's -2. -2 times 3, of course, is -6. Some number plus -6 gives us -1. That some number has to be +5. So +5 divided by 1 gives us +5. And so the oxidation state of iodine in iodate is +5. Now, again, normally halogens are -1, but we don't get down to the halogen rule until we've ruled out these other possibilities. So you don't assign halogen its oxidation state until you get to the end, until you get all the way down here. All right. So this one is called the chromate ion. So that is the chromate ion. And it is a polyatomic ion. The total charge on the chromate ion, of course, is -2. So -2 for the chromate ion. All right, when we look at this, is a monatomic ion present? And the answer to this is no. Remember, chromate is a polyatomic ion, so those oxygens are attached to the chromium atom. So that is a polyatomic ion. Is oxygen present? Well, yes, it is. So oxygen is present, so we'll put -2. -2, of course, times 4 is -8. -8 plus some number gives us -2. That some number, of course, has to be +6. We'll take that +6, divide by 1, and we get +6. So the oxidation state of chromium in chromate is +6. Now, that doesn't mean that the actual charge on chromium is +6. It just means that that's the oxidation state. All right, we're going to do one more. There are some 50 some odd of these on the naming review, but we're going to do one more, and then we're going to go to that in-class assignment problem. And so here we will go to this one, and this one is called dichromate. All right, so that is the dichromate ion. Dichromate, well, it's a polyatomic ion, and it has a total charge of -2, so we'll put that -2 over there. We'll look, is a monatomic ion present? And the answer is no. Is oxygen present? Well, yes, it is. So oxygen usually is -2. -2 times 7 is -14. Don't be worried that we got a big number there. To figure out chromium, we'll do -14 plus some number is -2. That some number, of course, has to be 12, +12. And then we're going to take the +12 and divide by 2. You can see now why I've been dividing by 1 on all of those. It's just to emphasize that we divide by the number of atoms here. So positive 12 divided by 2 is positive 6. So the oxidation state of chromium in dichromate is also positive 6. All right, and so now we want to go to, get this out of the way. We want to go over here to our document, but I'm going to make that big. All right. And let's see. No, that's not what I wanted. There we go. So here I've got the rules sort of right here beside. All right, and this is just in that these are the rules as they are listed, and I don't have the whole thing there, but anyway, you can see most of it. So element 0, monatomic ion charge, oxygen usually -2, hydrogen usually +1, halogens usually -1, and compounds adds up to 0, and polyatomic ions adds up to the charge on the polyatomic ion. All right, so we want to determine the oxidation number for each indicated element in each of the following substances. All right, so here we've got this neutral compound, COCl2. Turns out this is a covalently bonded compound. This is not ionic. So the total charge on this has to come out to 0. Since the total charge comes out to 0, we'll come over and look. We'll say, well, there's no monatomic ions present, which is there's no monatomic ions present, which is what Rule 2 says. Oxygen is present. Oxygen's -2. -2 times 1 is -2. And then let's see, our next rule, hydrogen is not present. Halogens, since we haven't assigned halogen yet, then we will put -1. -1 times 2 is -2. So that means to add up to 0, -2 plus -2 plus some number equals 0. That has to be +4. +4 divided by 1 is +4. All right, and that gives us the COCl2. So the oxidation state of the carbon there is +4. Next, here we've got permanganate. Total charge here is -1. Let's see, is an element by itself? No. Is a monatomic ion present? No. Is oxygen present? Yes. So -2. -2 times 4 is -8. Since we just have the one element left, we just need to figure out what manganese is. So some number plus -8 is -1. Of course, that comes out to +7. +7 divided by 1 gives us +7. So the oxidation state of manganese in permanganate is +7. Now, again, I don't want you to think that the charge on the manganese is +7. That is not going to happen. But the oxidation state comes out to +7. All right, next here we've got the hypobromous acid. It's a neutral compound, so the sum of all the oxidation states comes out to 0. The first rule, is it an element? No. Is a monatomic ion present? No. Rule 3, is oxygen present? Yes. Oxygen's -2. -2 times 1 is -2. Since we have 2 elements left, we're going to go back to the list, and you'll see here, right there, okay. Hydrogen is usually +1. So +1 times 1 is +1. So that means +1, -2, and some number gives us 0. That some number has to be +1. So the oxidation state of bromine here is +1. All right. Next, we have arsenic. Arsenic here is just elemental arsenic. That means it's 0 because Rule 1 tells us elements are 0. We don't have to go through the rest of it. So that is the oxidation state for this. On this one, it helps if you know what the name of this is. And the name of this happens to be called potassium peroxide. So this is potassium peroxide. And that gives you a hint that oxygen is not going to be normal in this case. So the total charge on all of this comes out to 0. So the total charge is 0. We look at the list, and on our list, is not an element. There are monatomic ions. Potassium is a monatomic ion. And because it is in group 1 right there, I had it hidden there. So because it's in group 1, it's positive 1. Okay, so I'll put positive 1 above the potassium. Positive 1 times 2 gives us positive 2. Some number plus positive 2 gives us 0. So of course that's negative 2. We'll do negative 2 divided by 2, and that gives us negative 1. So sometimes we can solve oxygen without getting to oxygen, without getting to the rule for oxygen. And if you look here on rule 3, right there, on rule 3 where it says except where it's bonded to itself, like in hydrogen peroxide, well, that's what we have going on here. All right, let's look at the carbon here in oxalate. That is the polyatomic ion oxalate. Has a total charge of negative 2. So that's the total charge of negative 2. And that's for oxalate. So now when we look, is a monatomic ion present? No, we already determined it's not an element by itself. Is oxygen present? Yes. Negative 2. Negative 2 times 4 is negative 8. Negative 8 plus some number gives us negative 2. That some number has to be positive 6. And then we'll do positive 6 divided by 2, and that gives us positive 3. So the oxidation state of carbon in oxalate is positive 3. The next one, this is hydrazine. This one's used in rocket fuel sometimes. All right, so here we go. Hydrazine has a total charge of 0. It's a neutral compound. We look up at the top. Is an element by itself? No. Is there a monatomic ion present? No. This is a completely molecular compound. Is oxygen present? No. Rule 4, is hydrogen present? Yes. We'll put positive 1. Positive 1 times 4 is positive 4. Some number plus positive 4 is 0. That has to be negative 4. Negative 4 divided by 2 is negative 2. So the oxidation state of nitrogen in hydrazine is negative 2. All right, finally here we've got nitrous acid, HNO2. All right, it's a neutral compound, so the sum of all the oxidation states will come out to 0. Is this an element by itself? That's rule 1. No. Rule 2, is a monatomic ion present? No. Rule 3, is oxygen present? And oxygen is present. So we'll put negative 2. Negative 2 times 2 is negative 4. All right. Next, since we have 2 elements left, we'll have to go back to the list. We'll see rule 4 there is hydrogen. So hydrogen, we've got positive 1. Positive 1 times 1 is positive 1. So 1 plus negative 4 plus some number gives us 0. Well, that some number has to be positive 3. Positive 3 divided by 1 is positive 3. So the oxidation state of nitrogen in nitrous acid is positive 3. Okay, so we now want to go back to our presentation, and we want to go back to the original presentation. All right, it took us a while to get through all of that, but well worth it. All right, so now that we've got oxidation numbers down, and we're feeling pretty good about that, we want to be able to determine what is oxidized and what is reduced in each redox reaction. So to do that, we need to look at the oxidation state on the reactant side of the reaction and the oxidation state on the product side of the reaction. And we can say that the element gets oxidized if it gets more positive. The element gets reduced if it gets more negative. And here's something important. if one thing gets oxidized in the reaction, something else necessarily has to get reduced. We can't have balanced regular equations without, if one thing gets oxidized and something else has to get reduced, we can't have one without the other. We always have to have oxidation and reduction going on at the same time. So here is an example. We've got methane that burns in oxygen to give us carbon dioxide and water. And I'll put the oxidation numbers here. There's hydrogen is +1. And if we go around, we'll figure out carbon is -4. Oxygen here is 0. In carbon dioxide, oxygen is -2, and that makes the carbon here +4. And then in water, oxygen's -2 and hydrogen is +1. So now that we've done that, we want to look at each element. We'll start with carbon. So carbon went from -4 to +4. So carbon got more positive, therefore carbon got oxidized. So carbon got oxidized. Again, it went from -4 to +4. It got more positive, therefore it got oxidized. It is not a coincidence that carbon has more bonds with oxygen. Typically, when things get more bonds with oxygen, they end up getting oxidized. All right, for hydrogen, hydrogen went from +1 to +1. It stayed the same, so it did not get oxidized or reduced. Oxygen went from 0 to -2, so it was -2 on both compounds over there. Since it got more negative, that means that oxygen got reduced. All right, so you just have to figure out what the oxidation numbers are for each element in each compound on both the reactant side and product side, compare them, and if the element gets more positive, it's getting oxidized, and if it gets more negative, it's getting reduced. Let's do another one. So here we've got zinc plus copper 2 sulfate, and it gives us zinc sulfate and copper metal. So zinc is 0, the copper 2 sulfate, copper is +2, oxygen comes out to -2, and then the sulfur comes out to +6. I'm not really going to go through that one in great detail. I'm just going to say if you're still having trouble doing oxidation numbers, go back and practice the previous part. The next thing here, over here on the right, we've got zinc sulfate. Zinc is +2. Again, oxygen's -2, sulfur is +6. And the copper on the right is 0. So now we just need to look at each element. All right, zinc went from 0 to +2. Because it got more positive, it got oxidized. So zinc was oxidized here. Carbon went, copper went from +2 to 0. It got more negative, therefore copper got reduced. And we'll find that the other two elements don't change. So the other two elements don't change. So next, we want to figure out what is getting oxidized. We're going to go to this in-class assignment problem. Which element is oxidized and which is reduced in the following reaction? So we'll put the oxidation numbers immediately above it. So 0, 0, -1 for the chlorine, +2 for nickel. So on this one, nickel went from 0 to +2, and chlorine went from 0 to -1. So we need to figure out what was oxidized. Well, the thing that got more positive was oxidized, so nickel was oxidized. All right, and the chlorine got more negative, and therefore it was reduced. So it was reduced. All right, on this next one, we've got iron nitrate, and it's iron 2 nitrate. So we know that this iron has a +2 charge. That's because nitrate is -1, and there's 2 of them, so that has to be +2. And we can figure out the oxygen and the nitrogen in this compound, or we could pull the nitrate out and solve it by itself. And so we nitrate NO3 minus, and we say, okay, total charge is -1, -2, -2 times 3 is -6. That'd be +5, +5. So the nitrogen and nitrate is +5, and the oxygen is -2. Aluminum here, nothing to solve. That one's 0 because it's an element. Same thing here. Iron is 0. Aluminum, it's in a compound, it's +3. And then for nitrate, because it's the same, nitrate's the same polyatomic ion, it's +5 for the nitrogen and -2 for the oxygen. All right, now that we've done that, let's go through and look at each element. So we'll do iron, nitrogen, oxygen, and aluminum. Iron went from +2 to 0, so +2 to 0. Nitrogen went from +5 to +5. Oxygen went from -2 to -2. And aluminum went from 0 to +3. So the thing that got more positive is the thing that got oxidized. Well, it looks like aluminum got more positive, so aluminum was oxidized. And the thing that got more negative is the thing that got reduced, and iron got more negative, so iron was reduced. Nitrogen and oxygen didn't change in this particular reaction, so their oxidation states didn't change. They neither got oxidized nor reduced. Okay, so now let's figure out this. This is lead 2 sulfide. Sulfide are -2, and lead is +2 in that case. This is hydrogen peroxide. And in hydrogen peroxide, the hydrogen is +1 and the oxygen is -1. So it helps if you recognize that that is a peroxide. This is lead 2 sulfate. So the lead is 2+. Sulfate, the oxygen is -2. The sulfur is +6. And then here for water, +1 on the hydrogen and -2 on the oxygen. So now we will just list all of these. So we've got PB, S, H, and O. All right, lead on the left is +2, and on the right is +2. So +2 to +2, no change. Sulfur, -2, and on the right it is +6. So big change there. Hydrogen +1 and +1. So hydrogen didn't change. And oxygen went from -1 to -2. They're all -2 over there. So -1 to -2. So the thing that got more positive clearly was the sulfur. So sulfur was oxidized. All right. And the oxygen got more negative and went from -1 to -2. So oxygen got reduced. So oxygen got reduced. All right, so that is that set of problems. All right, and we still have a little bit left to do in this section. So even though the video is getting kind of long, I'm going to return back to our presentation. We're going to do the part on activity series, and then we'll wrap up that video before we move on to the next section. All right, so there are several different types of redox reactions that we want to be aware of. There are combination reactions. Combination reactions, we saw this before in chapter 3, where we have two substances combined to form a third substance, so they form a new substance. And here is an example. Sodium plus chlorine gives us sodium chloride. We had one on that in-class assignment that we just saw. Nickel plus chlorine gives us nickel chloride. That's a combination. Okay. All right, so that's a combination reaction. Magnesium plus nitrogen gives us magnesium nitride. When you do the lab on campus, we actually do this experiment where we take magnesium and we actually heat it up with oxygen. But one of the byproducts is because there's a lot of nitrogen in air, you can get some magnesium nitride. So that's kind of an interesting byproduct. But again, that is a combination. So two things becoming one in that case. Here is an important note. Not all combination reactions are redox reactions. So not all combination reactions are redox reactions. And to explain that, let me go back over here. And I just want to show you an example of a combination reaction that is not a redox reaction. And so I'll do calcium oxide plus carbon dioxide gives us calcium carbonate. And if you look, you will see the oxidation number. So +2, -2 for that. We've got -2 for the oxygen and +4 for the carbon. And then for calcium carbonate, we'll +2 for calcium, -2 for oxygen, and +4 for the carbon. You'll notice here the oxidation states don't change. And if the oxidation states don't change, it's not a redox reaction. So if the oxidation states don't change, it's not a redox reaction. So it's always worthwhile to check those oxidation states to make sure that your reaction is really a redox reaction. If I ask you a question, is this a redox reaction? Then the answer isn't going to be, well, it looks like a combination, so yes. No, the answer is I'm going to look at the oxidation states and let that tell me. And if the oxidation states change, then yes, it's a redox reaction. Also remember that you have to have both an oxidation and a reduction occur for it to be a redox. Okay, so next we also have decomposition reactions. Decomposition reactions are sort of the evil twin of combination reactions, or the alter ego, if you want to put it that way. And that's where you have a single compound that breaks apart to make two or more substances. So for example, if you have ammonia can break apart to make nitrogen and hydrogen. Mercuric oxide or mercury 2 oxide can break apart to make mercury metal plus oxygen gas. Not one that I recommend doing around the house because that's really poisonous. All right. And just as a note, just like what we saw, not all decomposition reactions are redox reactions. And just to illustrate that point, again, I'm going to pick something that we can look at, and that is, let's look at, all right, we'll do this one. We'll do H2SO3, which is sulfurous acid. And if it gets to too high of a concentration, it will break apart and make water plus sulfur dioxide, SO2. And as we saw in that section about gas producing reactions, as we saw in that section, that is what's happening there. That's a gas producing reaction. I'm going to write down the oxidation states real quick. So -2, +1, and then this comes out to +4. All right, so make sure I got that right. Yes, and then -2 and +1, and then -2 and then +4 are the oxidation states there. So as you see, the oxidation states don't change, so that is not a redox reaction, but it's definitely a decomposition reaction. I point that out because, again, in order for something to be a redox reaction, the oxidation numbers have to change. All right, we're going to look at combustion reactions. And we've seen some combustion reactions. I showed you methane burning a little bit ago. Here we've got C4H10 burning in oxygen to give us carbon dioxide and water. We have another fancy name for this. That was butane, but another fancy name for this, we also call it burning, right? So we burn it. And we will find that all of our combustion reactions are redox reactions. All right, so this will just take a minute, but look at that compound, C4H10. So C4H10, I'm going to write it down on this other piece of paper. So C4H10. We're going to figure out the oxidation state for this, and you may kind of have your mind blown here. All right, so +1 for the hydrogen times 10 is +10. So, and the whole thing comes out to 0. So this has to be -10, and -10 divided by 4 is 2.5, negative I made a mistake there, negative 2.5. So the oxidation state of carbon in butane is negative 2.5? Well, yes, it is. And the reason for that, I'm going to draw. Now, we haven't done Lewis structures, so don't freak out if you don't get this. I'm going to draw butane here. And so here you'll notice that on this butane, there are two different types of carbons. There are carbons that have 2 hydrogens attached and carbons that have 3 hydrogens attached. Well, the oxidation states of the carbons with 3 hydrogens attached is negative 3. So these are negative 3. The oxidation states of the carbons with 2 hydrogens attached, those are negative 2. But they average out to become negative 2.5. I just like to point that out because it's kind of cool. So I'm going to go back over here. All right. So displacement reactions. Displacement reactions, that's where an element reacts with a compound and that element displaces another element in the compound. So here is an example of this. If you take zinc and put it into hydrochloric acid, you will find that you'll form zinc chloride plus hydrogen gas. You'll see in this reaction, zinc is getting oxidized and hydrogen is getting reduced. So yes, zinc getting oxidized, hydrogen getting reduced. If we look at another one here, zinc metal plus copper 2 sulfate gives us zinc sulfate plus copper metal. Well, you'll see that the zinc is going from 0 to +2. The copper is going from +2 to 0. So zinc is getting oxidized, copper is getting reduced. In both of these cases, zinc is replacing some other element in the compound. We call these displacement reactions, and you'll sometimes see these called single replacement reactions. We'll find that these displacement or single replacement reactions are always redox reactions. So oxidation states are always going to change here. So here is a picture of what this looks like. Again, if you're taking your lab on campus, which hopefully in the future we'll get to do that again. If you're taking your lab on campus, then I know that we do this experiment. We do this in lab where we take zinc metal and we put it into copper 2 solution. We can tell, here, I'm going to put the compounds down here. We can tell that this solution is copper 2 sulfate. Copper 2 has a distinctive blue color to it. Sometimes it's green if it's in a different compound, but usually it's either blue or green. And so we get this blue color to it, and we've got zinc metal here, and the zinc metal reacts with the copper 2 ions. Now the sulfate is just floating around. We'll find those sulfates are spectator ions. If you're feeling courageous, dissociate this and this to give you a complete ionic equation, and then cross out sulfates and you'll get your net ionic equation. All right, we're not going to practice that because we've done enough of those net ionic equations for this lecture. Okay, so let's see. You'll notice over here on the product side that it's getting less blue because the concentration of the copper 2 is going down, and that you're getting this sort of brown stuff. Well, that brown stuff, it looks kind of black here, but it's really brown, is the copper metal. And that is what's going on. If you were to isolate all that brown stuff and dry it out, it would look kind of a reddish brown color, kind of like a penny, which is also made out of copper. Well, mostly. Well, it's complicated. All right. All right, yes, and here I'm putting the oxidation states in. So zinc is going from 0 to +2. Copper is going from +2 to 0. All right, well, we find that this is a spontaneous reaction. And what spontaneous means is it happens all by itself as long as nothing is in the way. So kind of like if you take a ball and put it at the top of the hill, it will roll to the bottom of the hill as long as it doesn't get stuck on something. And getting stuck on something, usually that's a kinetics issue. So what we're talking about is it will roll to the bottom of the hill, again, as long as nothing gets stuck in the way. So that's what we mean by spontaneous. All right, so this is a spontaneous reaction, much like a ball rolling down a hill is spontaneous. However, if we take copper metal and put it into a solution of zinc sulfate, we get no reaction. Just in the same way that if we put a ball at the bottom of the hill, it does not spontaneously roll to the top of the hill unless somebody is pranking you, right? So the way that we can predict whether a reaction is going to occur is to look at something that we call the activity series. The activity series is a tool that we use to solve this kind of prediction problem. We will find that in the second semester, I will give you an updated version of this, an updated tool that actually uses numbers. So then we can dispense with the activity series and go with numbers. But for now, we'll just say the activity series will help us predict this. And let me show you how this works. So this is the activity series. Before I discuss this, there's a couple of things I want to point out about the activity series. The first thing is that you'll notice that all of these things are metals except one, and that is hydrogen. So all of these substances here are metals except for hydrogen. You'll also notice that all of the substances are neutral elements on the left side of the chemical equation, and they are charged ions on the right side of the equation. So in other words, all of these are oxidation reactions. We actually call these oxidation half reactions, but we'll save that half reaction talk for second semester. Okay, so if I were to ask you the question, which one of these, let's say I am going to give you 1 ounce of any of these, which one are you going to ask for? I'll give you a second to think about it. And by the way, I'm not really going to give you a full ounce because I don't have that kind of money. All right. Hopefully you said gold or platinum. Now, I don't know which one is more valuable right now. I could go look it up, but I'm not going to do that. I don't know which one is more valuable. Lately, platinum has been kind of expensive, but it changes. Sometimes gold is more expensive. Sometimes platinum is more expensive. But the thing about gold and platinum that we really like is, one, they're really pretty, right? They're shiny, and they stay shiny pretty much forever. And that's because they are extremely unreactive. So gold and platinum are extremely unreactive. Well, you'll notice that they're way down here at the bottom of the list. All right, so they're way down there at the bottom of the list. So they are the least reactive, or in the terminology that we use for this, we call them the least active. As we go up the list, these things get more and more reactive. So for example, silver, it's still not very reactive, but if you leave silver out, it will get tarnished. And what's happening when silver gets tarnished is that it's reacting with some of the sulfur that's in the air, and you'll get silver sulfide. And so that happens. Same thing with copper. Copper's pretty unreactive. However, if it's exposed to the elements, it'll eventually get that green patina, kind of like the Statue of Liberty has that green color to it. That's copper. What is it? That's copper carbonate that is on the surface of the Statue of Liberty. When the Statue of Liberty was first made, it would have been shiny. Wouldn't that have been cool to see? All right. I wish I could go back in time and see that. All right. Hydrogen is here because, well, I'll show you how hydrogen works here in a moment. But all of these elements are going to be more reactive. And in fact, anything above hydrogen will react with H+. And H+, as we learned in the previous section, is really just acid. So all of these things that are above the hydrogen will react with the hydrogen ion. And then as we go to the top of this list, we will see that we get things like lithium and potassium, and they are extremely reactive or extremely active. All right, so again, the way that you use the activity series is that elements will react with the ions that are below them. As I've already mentioned, any of these metals will react with the hydrogen ion. In other words, they will react with acid. The elements down here will not react with acid. So if you take copper and put it to acid, that itself won't be enough to react with the copper. Now, if there's some other stuff present, you can make that happen. Silver won't react with regular acid. You have to use like nitric acid to make that happen. Gold, it won't react with either of those. In order to get gold to react with acid, you need to have concentrated nitric acid and add a lot of HCl gas into it. They call that aqua regia. Anyway, it's really, really difficult to react gold and get to the gold 3 ion. But the point of this is that elements will react with the ions below them, and the elements will not react with the ions above them. So for example, in the one that we saw a little bit earlier, zinc will react with copper 2 ion, but copper will not react with the zinc ion. So here we go. So here's zinc. It will react with copper 2, but copper will not react with zinc 2. And it doesn't really matter how far apart they are or how close they are. Cobalt will react with nickel 2, but nickel will not react with cobalt 2. So that's all it takes. All right, we're going to look at number 56 on the in-class assignment, and we'll have to kind of switch back and forth between the activity series and our problem, but we can handle this. So let's go to our in-class assignment that is right here. Okay, so let's see. Nickel metal is added to a solution of copper 2 nitrate. So let's write down what the substances are here. So we've got nickel solid, and we're putting it into copper 2 nitrate. And copper 2 nitrate is CuNO3 2. And that one is aqueous. So we want to determine so here is our element, and copper 2 is our ion. So will nickel react with copper 2? Well, we're going to go back to this list, and we look here, and we'll see nickel is here. There's copper 2. So yes, nickel will react with copper 2. So yes, we'll get a reaction. Oh, by the way, let's go back and look. Nickel, when it gets oxidized, will form nickel 2. That'll make the stoichiometry really easy here. So we'll end up with nickel NO3 2 AQ plus copper solid. It turns out on this one it'll already be balanced. So these will all be 1. So that one's already balanced. So the activity series says yes, a reaction will occur. And if no reaction occurs, then we'll just put NR. So let's look at this next one. Hydrochloric acid is added to gold metal. Well, hydrochloric acid is HCl, AQ. We're going to add that to AU, solid. And we want to determine, will a reaction occur? Okay, so our element here is gold, and the ion is H+. Let's go back to our list. Here's gold, and there's H+. Since gold is below H+, no, a reaction will not occur. So we're going to put no reaction, NR. That's what it asks us to put, NR. All right, next we've got chromium metal. It is immersed in an aqueous solution of cobalt 2 chloride. So chromium metal, and we put it into a solution of cobalt 2 chloride. So cobalt 2, it'll be CoCl2 AQ. All right, so chromium metal is immersed in an aqueous solution of cobalt 2 chloride. So now we need to go back at our list. Our element here is chromium, and our ion is cobalt 2. So I'm going to go back to our presentation, and chromium is here, and cobalt 2 is there. So chromium is above cobalt 2, so yes, it will react. Now, before we switch away from this page, you'll notice that when chromium gets oxidized, it forms chromium-3. Now, that's not a big deal. We can handle that, but it is going to change the stoichiometry just a little bit. So it will become chromium-3 because of that. So when we form chromium-3 chloride, it'll be CrCl3Aq, and then plus cobalt solid. All right, so now that we've done that, let's go ahead and balance the chlorines first. Even though chlorine is the smallest element here, let's go ahead and balance the chlorines first. So we've got 3 chlorines there, 2 chlorines there, and the way that I'm going to approach this is that I'm just going to do the least common multiple. So the least common multiple of 3 and 2 is 6. So here I'll put a 2 there, that'll give us 6 chlorines, and I'll put a 3 there. And then now when we balance this, we'll get 3 cobalt atoms, and over here we'll have 2 chromium atoms. All right, our last one, hydrogen gas, so H2 gas, plus is bubbled through a solution of silver nitrate. So AgNO3. If you remember, silver has a charge of +1 when it's in a compound. So hydrogen, our element here is hydrogen, and silver ion is the ion that we're interested in. So we're going to come back over here. Here we've got, there is the hydrogen and there is the silver ion. Since hydrogen is above silver ion, it will form the silver, it will react. So hydrogen will get converted into H+, and the silver ion will get converted into silver metal. All right, so we're going to go back. So the hydrogen gas will get converted into hydrogen ion. So hydrogen ion plus nitrate is just going to be nitric acid. So we will get HNO3 AQ plus Ag, and that gives us Ag solid. All right, here it looks like almost everything is balanced except for the hydrogen. So we could either put a half here, or we could just balance the hydrogen right up front. Put a 1 there, a 2 there, and now let's balance the nitrogen by putting a 2 here, and balance the silver by putting a 2 there. And now it's balanced. All right, well, that is the end of the section that is that talks about oxidation and reduction reactions. All right, so I'm going to go back over here. So that is the end of that section, and that'll be the end of this video, because this video is already over an hour. Our next video is going to be about concentrations, and you'll want to make sure your calculator is all warmed up and ready to go.